Carbon's physical properties are dictated by the three-dimensional arrangement of its atoms. Diamond is a rigid tetrahedral grid, the hardest natural material on Earth. But when those same atoms form flat two-dimensional sheets, they become graphite, soft enough to rub off on paper. We no longer have to wait for nature to produce these atomic arrangements. Using quantum mechanical simulations, researchers can design and test new structures inside supercomputers, measuring their precise properties before a physical version ever exists. A study published in Academia Quantum has revealed the theoretical engineering of a stable three-dimensional form of carbon known as yne C16. Yne C16 represents a departure from carbon's known behaviors. It is a 3D cubic crystal, yet it lacks the extreme hardness expected of its form, behaving instead like a highly compressible soft metal. To understand this discovery, we have to look at the molecule that preceded it, SRS-C8. While this body-centered cubic model was a significant theoretical step, it contained a structural flaw. In this projection, you can see the discontinuous, broken atomic arrangement where the polyhedra failed to fully connect. This chart maps the acoustic vibrations of SRS-C8. As the highlight moves to the bottom of the plot, you can see the red lines dipping below the zero axis. These are negative acoustic phonon modes, meaning the molecule's own internal vibrations would shake it apart in the real world. A lattice must be able to survive its own quantum vibrations to be considered dynamically stable. To move from a computer model to a viable state of matter, the 3D lattice required a different geometric approach. Researchers solved this by combining two distinct bonds, distorted tetrahedral bases found in diamond connected by linear triple bonds. This shape mirrors phosphorus trichloride, forming a pyramid where the stable carbon base and the apex triple bond mimic a high-density electron lone pair. This is the finalized unit cell of yne C16. In this diagonal projection, the brown carbon bases are locked together by the white carbon triple bonds. The gaps that destabilized previous models have been closed. Placing the linear chemistry of a triple bond into a dense 3D lattice changes the way force and electricity move through the crystal. Researchers use density functional theory to validate this new geometry. This quantum modeling method calculates the exact distribution of electron charge throughout the new lattice. As shown in this charge density projection, the triple bonds are surrounded by large yellow volumetric envelopes. These yellow volumes indicate a high concentration of electron charge, providing the cohesive strength necessary to hold the structure together. This chart proves the molecule has overcome the flaws of its predecessor. Every red frequency line remains strictly above the zero horizontal axis, indicating that its vibrational frequencies are fully positive. Having passed these computational stress tests, yne C16 is a mathematically verified state of matter. Despite its 3D structure, yne C16's geometric distortions create a mechanical paradox. It has a Vickers hardness of only 10 gigapascals, making it highly compressible and ductile. It is an incredibly soft form of carbon. The material also exhibits unusual electrical properties. In this band structure plot, the blue energy lines pass directly through the central red Fermi level. This indicates that the hybrid bond structure creates pathways for electrons, giving the crystal weakly metallic conductivity. The stability of yne C16 proves that even a single well-studied element like carbon can be structured into forms with unexpected physical behaviors. While yne C16 currently exists as a quantum projection, its high-symmetry cubic space group suggests it is a viable candidate for future synthesis. Advancements in diamond fabrication may eventually move this material from a supercomputer into the real world. If you want to see more breakdowns of materials that shouldn't exist, like and subscribe, and let us know what we should cover next in the comments. Today's video was brought to you by Synestec Systems LLC, founded by Shane Persinger.